Hi everyone, welcome back to the biochemistry series for cellular respiration. So this time we're going to be covering the concept of redox reactions, as well as the purpose of electron carriers, both of which are very important concepts that we need to cover first before we can delve into the processes of the sub-processes of cellular respiration. So to start things off, I want to first review the basic terminology of redox reactions or oxidation-reduction reactions. So when a compound is losing electrons, we call this compound or atom is losing electrons. We refer to this molecule, compound or atom, as being oxidized. Whereas if a compound, electron, or molecule is gaining electrons, we refer to this as a molecule that's being reduced. Now, when a compound loses electrons, we also refer to this as the reducing agent or the reductant. Whereas with a compound that is gaining electrons, we refer to this as the oxidizing agent or oxidant. Okay, so we can determine the oxidation level of a compound based on the constituents of the molecule present. So we refer to here, or rather than the oxidation level of a compound, we're referring to the oxidation level of oxidation of the central atom, which in this case is the carbon molecule. So we can see here that the number of electrons owned by the central red carbon increases as we go up this list of molecules, right? Whereas we can see that the oxidation level of the central atom increases going down. Now, there are several key details to understanding this. We can see here that the carbon atom is greater than the hydrogen atom in terms of electronegativity. So the carbon atom will take ownage of the two bonding electrons. So we see here that although that there is a covalent bond shared between the two atoms, there isn't necessarily equal sharing of electrons between the two atoms, which is why we would refer to this as polar covalent bonding, where one atom tends to, in a sense, steal the take ownage of the electrons relative to the other participating atom. So in this case, between the carbon and the hydrogen, we can see here that the carbon will tend to take most of the electrons, right? So on the other hand, we show that we see, or in the middle, in the intermediate stage, we see that, or at the intermediate, the middle, not the middle, the another example would include that carbon-carbon bonds. We obviously know that because they're both the same atom, that they would share electrons equally. But in the case of oxygen atoms, because oxygen atoms are greater than carbon atoms in terms of electronegativity, the oxygen atom will tend to take ownage of all the bonding electrons between itself and the carbon slash hydrogen partner, right? So we can see here that in carbon dioxide or CO2, we can see that although the carbon atom is participating in two double covalent bonds with oxygen, all those electrons belong to oxygen and none of them necessarily belong to carbon. Hence the reason why it has such a high oxidative state. And we see that the carbon atom actually has actually owns zero of the electrons. We're just looking at the ownership of the carbon atom, the ownership of electrons of the carbon for the carbon atom in particular as a central atom. We can see here in another example that there's a CC bond, a CC single bond, right? So we can see that these electrons are shared equally. So this carbon atom actually has an electron, owns one electron. The other 6 electrons belong to the 2 oxygen atoms. This oxygen atom owns 4 of the electrons, all 4 of the electrons in this double bond, and this oxygen atom owns 2 in this carbon oxygen single bond atom. In carbon monoxide, we see here that there's 6 electrons participating in a covalent bond, but all 6 of them will belong to this oxygen atom. So on and so forth. I think the general idea becomes a little more clear once you get a familiarity with it, with these concepts. Moving on, there are 4 ways electrons are transferred between compounds in biological conditions. So the first way is electrons are directly transferred as electrons. If we take a look at this example here, we can see that iron and copper are we can see that iron and copper participate in a redox reaction, but we have to think of these as conjugation pairs, where one of them is where iron is the one that's being oxidized and copper is the one that's being reduced, right? Because we can see that the oxidation state of iron increases from 2 to 3, right? Because it loses an electron here. And then this electron participates in the second reaction where copper is reduced by this electron, forming copper plus, right? So in this case, we can see that iron here tends to be the reductant, and copper is the oxidant. Just give me a second. Let me make sure I reference these atoms correctly. Yes, I got that correct. So alright, that is iron, and then copper is... Yes, so I'm correct. Now, as hydrogen atoms, so this is the second way that electrons are transferred. They can be transferred as hydrogen atoms, where two arbitrary compounds, A and B, right, are transferred as, or A and B, where A contains 2 hydrogen atoms and B has none. But we can see that once the reaction completes, on the product side, we can see that B contains the hydrogen atoms. So if we refer to these as half reactions, we see here that A will be oxidized and lose 2 hydrogen ions plus 2 electrons, and then these 2 hydrogen ions and 2 electrons will participate in the second reaction where B will be reduced, in the process gaining 2 hydrogen atoms. In this case, we clearly observe here that A is the reductant and B is the oxidant. Now, the third method of way electrons are transferred as hydride ions. This form of electron transfer happens particularly in the case of any NAD or nicotine adenine dinucleotide linked hydrogenase. So in the terms of this particular electron carrier, which we'll go through later, electrons are transferred between NAD and some sort of arbitrary molecules through hydride ions, which is just a negatively charged hydrogen ion which contains 2 electrons. And then the last method of electron transfer is where there is direct combination between oxygen and a variable hydrocarbon. So we see here that this variable hydrocarbon right here with the CH3 group is the reducing agent, and then we can see here that the oxidizing agent is the O2 molecule, right? And then we see here that once the 2 molecules mix, or once the 2 molecules participate in reaction, we observe that this that this portion of the hydrocarbon here is actually oxidized, right? Because even though it still contains eight electrons, two of those electrons now belong to the oxygen, which is in this case reduced, right? And in this case, because it's participating in a bond with carbon, carbon loses those oxygens. Thus, we call this this carbon here oxidized. Okay. Now, we also need to go through the term of reducing equivalence, which is where an electron participating in an oxidation-reduction refers to the electron participating in an oxidation-reduction reaction. And these electrons can be in the form of an actual electron, as shown here in example 1, and then a hydrogen atom, which is shown in method 2, and then a hydride ion as shown in method 3. Okay. Now, let's go through. Oh yes, we need to define like a major enzyme that facilitates a lot of these reactions, because these reactions don't necessarily happen on their own. They're facilitated by some sort of enzyme that catalyzes the oxidation of compounds, as well as the reduction of compounds. So this is what we call these enzymes oxidoreductase or dehydrogenase, where the removal of hydrogen occurs from a compound, or electrons from a compound. Now, there are coenzymes or cofactors are non-protein compounds that are necessary for the functioning of an enzyme. So, in the case of metabolism, they serve as universal electron carriers that results in the conservation of free energy released by some sort of substrate. In this case, in the case of cellular respiration, glucose, which is oxidized, right? Or yeah, where glucose is oxidized, and in the process of doing so, it releases free energy, and that energy somehow needs to be conserved, and that's what these universal energy carriers, or these universal electron carriers, serve as. They serve as electron carriers that conserve free energy to be later used for endergonic reactions, as I described in the previous video. Now, there are several coenzyme factors here that are worth noting. So the first one is a big one, which is nicotine NAD, NADP, FMN, FAD, and these are water-soluble coenzymes that undergo reversible oxidation-reduction reactions or electron transfer reactions in metabolism. So NAD and NAD/NADP move readily from one enzyme to another, and a key thing here, actually, in terms of nutrition, we find that NAD or NADP is actually a derivative of the vitamin niacin B3, right? So vitamin B3 or nicotinic acid is essential for synthesis of NAD or NAD and or NADP, which is the reason why it's important to obtain niacin or vitamin B3 in your diet. The same thing with FMN and FAD, which is flavin adenine dinucleotide. In contrast to NADP or NADP, or NAD or NADP, they are very tightly bound to enzymes and serve as some sort of prosthetic group, and this is what we call flavoproteins, right? Now FAD and FMN are actually derivatives of the vitamin riboflavin or vitamin B2, right? Which is also another important vitamin to include in your diet, right? Quinones are lipid-soluble enzymes that act as electron carriers and proton donors in the non-aqueous environment of membranes or inner mitochondrial membrane, right? So one such example of quinones are ubiquinone, which is coenzyme 10 or COQ10, right? Iron-sulfur prosthetic groups are present on iron-sulfur proteins that undergo reversible oxidation-reduction reactions and therefore also serve as electron carriers. There will be plenty more examples to show below later down. But for now, I want to shift our focus and not shift actually. I want to look deeper at these two molecules, NAD and FAD. Okay. So with NAD versus NADPH or nicotinic acid adenine dinucleotide, right? We see here that the name in itself is relatively explanatory. We can see that there are two nucleotides. There's one over here, and then there's another nucleotide over here present. Okay. We can see that there's the adenine base, or the nitrogenous base, which is the adenine itself, and then this is the nicotinamide ring, which is derived directly from vitamin B3, that as we saw earlier, right? So this is NAD. Okay. On the other hand, we have the NADP, and the reason why it's called NADP is because there's a phosphate group at this carbon over here, at carbon number 2 of the ribose sugar, of this ribose sugar here. So in terms of similarities, both NAD and NADP contain a nicotinamide ring. They both contain adenine. They're comprised of two nucleotides connected by a phosphodiester bond, which is an atypical linkage relative to nucleic acids. And then the difference is that they, instead of a hydroxyl group on C3, like in NAD, NADP carries the phosphate group. And they also have differences in function. So overall, both of them share the same, NAD shares the function, NAD and NADP both share the function where the nicotinamide ring functions to carry electrons, right? This is actually, we'll go through this reaction in a bit on how the electrons are carried for this ring, but for now, just understand that the nicotinamide ring functions to carry electrons. On the other hand, in terms of differences, NADH or NADH or when it's reduced, NADH functions in catabolic reactions, in essence glycolysis or acetyl-CoA synthesis or TCA, right, or the citric acid cycle. On the other hand, NADPH NADP in its reduced form, or NADPH, functions in anabolic reactions such as the Calvin cycle. Now, let's take a closer look at NAD and NADP. So a key thing that we want to actually focus on and actually really observe here is the nitrogenous, or not the nitrogenous, or it is nitrogenous ring, nitrogenous base. We need to take a look at this because this is the key part of the of NAD that actually participates in the redox reactions. Okay. Everything else here we can just consider as R for now when I explain the reaction. So the reaction in its summarized form is NAD positive plus 2 electrons plus 2 hydrogen atoms will get you NADH in the form of a hydride ion plus H. So the reaction mechanism, it's not necessary. So I want to go through the reaction. I also want to, so with this in mind, I actually want to go through the reaction mechanism of how this entire thing works. Now the reaction mechanism is, it's not necessarily important to note, but make sure to pay attention to the nitrogen, or in essence the carbon, or pay attention to the nitrogen. The carbon opposite or para relative to the nitrogen, and the so sorry, just give me a second here. What we want to pay attention is to the nitrogen, the carbon opposite relative to the nitrogen, and the hydrogen and the hydride ion formed, which is is shown here. So we take a look at the carbon, which is opposite, literally opposite from the nitrogen. There's the nitrogen itself, and then the hydride ion that forms. So let's take a look at the individual mechanism shown here. So the oxidation of NADH. So we see here that electrons are pushed. We see an arrow pushing mechanism shown here, where the electrons are pushed here, these ones are pushed here, which is essentially allowing the electrons to be, or we essentially cause the formation of a leaving group, right? And what forms here is that this hydride ion will attack some sort of alcohol or some sort of ketone, and what we're left with, we see a nucleophilic attack from the hydride ion, which allows for a proton transfer from some sort of acidic base, from some sort of protonated base, right? And we see here that once this reaction goes to completion, we see that the nitrogen now has a positive charge present on it, and hence the reason why we see this as NAD+, right? And then we have a reduced alcohol plus a deprotonated base. Just an important details to note: the NAD plus on the positive, the positive charge in that the positive charge superscript indicates that the nicotine amide ring, more specifically the nitrogen, is positively charged, not the entire molecule. In fact, we can see that the entire molecule, if we look at the molecule specifically, we can see that there's more negative charges than there are positive, right? So, and this is, it's unclear about the actual mechanism, but we know that a hydride ion reduces nicotine amide adenine dinucleotide, and the second hydrogen proton is released to the aqueous solvent, in essence the matrix, based on the summarized reaction. Is released to the aqueous solvent. So this small detail here, the matrix, this is just essentially referring to the mitochondrial matrix. Honestly, I'm not entirely sure about that detail there. That might actually need to be reviewed, but for the most part, I do believe that that the chemical logic that proposed here is sound, because I actually got this information here from the David Klein organic chemistry textbook. Okay, so yes, we have to go through the reduction of NAD. So this is the opposite mechanism. So I would assume that some sort of base, probably the same base, will nucleophilically, or not nucleophilic, there will be a proton transfer, so this base becomes protonated here, right? And this allows an arrow pushing mechanism that allows the hydride ion to reform, and that hydride ion will then again serve as a nucleophile and attack the carbon atom that's para or opposite from this nitrogen atom, which causes another arrow pushing mechanism, right, to reform the positive base. Oh, this is, I messed up. This is not correct. There we go. There should have been a positive charge here, right? And then we find that the ketone or aldehyde that was once formerly an alcohol was oxidized with NADH being reduced. Okay? So that's essentially the entire process of how NAD and NADP work at the molecular level. There are other electron carriers. I want to take a look next at flavin adenine dinucleotide and flavin mononucleotide. So essentially here we're taking both flavin adenine dinucleotide and flavin mononucleotide, they both contain what's called the isoalloxazine ring derived from riboflavin. So the key difference is that in FMN, in flavin mononucleotide, the hydroxyl group is replaced by a phosphoryl group. In flavin adenine dinucleotide, this hydroxyl group is replaced by an adenylyl group. Okay? That, if you can just picture that. Yeah. Flavin mononucleotide, we can see that this big portion here, the isoalloxazine ring, is the one that undergoes redox reactions. Everything here isn't necessary for the oxidative redox reactions. Yeah. Oh, another key detail here, another interesting detail here that I found was that this long hydrocarbon chain is actually just an uncyclized ribose. Yes. Yeah, so here's the difference between flavin mononucleotide and flavin adenine dinucleotide. So we see here that flavin mononucleotide contains a phosphoryl group, and then FAD contains the adenylyl group. Hence the reason why it's called flavin adenine dinucleotide. Okay. Now, this is the overall summarized reaction for reducing flavin mononucleotide and flavin adenine dinucleotide. So, in its oxidized state, this is how FAD or FMN exist. Upon reduction from one hydrogen atom and electron, we see that it's partially reduced. So it can exist. So unlike NAD, FAD can actually exist in a partially reduced state. However, to fully reduce it, there needs to be another nucleophilic attack where FAD and FMN are reduced twice to be fully reduced. Okay. So in the process of this, we observe that the method of electron transfer is different compared to electron transfer for NAD. Electrons are transported in the form of hydrogen atoms, not hydride ions. FMN and FAD are capable of accepting either one or two electrons, and this allows the coenzymes to participate in a diversity of chemical reactions. Right? Alright. Now, another electron carrier that we want to take a look at are quinones, which are lipid soluble. So they're soluble in lipids. Right? So ubiquinone or coenzyme Q or Q are lipid soluble benzoquinones containing a long isoprenoid side chain. So essentially this side chain right here. I've simplified it for your sake, for viewership, but essentially what happens here, right, is that it's a long repeating chain. So if I draw this out, it's just essentially this. Yeah, I believe it would be something like that. Oops. H. H. Yeah. Yeah, and so on and so forth. I think you guys get the idea. I think I might have messed up the chemical formula here, but it's just repeating units of whatever this is. Right. An isoprene. And I think an isoprene was something like this, right? Or no, that's a terpenoid. But yes, this is just the repeating unit here. Now, like flavin prosthetic groups or cofactors, they receive electrons in the form of hydrogen atoms, or hydrogen atom plus electron, or as we saw in FAD and FMN, they exist like as a hydrogen atom with one electron present. So in its normal form. And therefore they are functionally capable of acting as a medium between a 2 electron donor and a 1 electron acceptor. So 1 electron acceptors would include FAD, FMN, and then a 2 electron donor could be NAD. Okay. Now, here's the overall reaction shown. So ubiquinone in its fully oxidized state can be reduced. Yeah. Ubiquinone can be fully reduced, can be partially reduced, where we see this oxygen in its partially reduced form, as well as this vinylic alcohol that forms an enol, right? And then once another electron is added, we see here that 2 alcohols are formed, right? Now the mechanism that actually describes this is not fully shown. I'm not fully sure if there is a mechanism for this that's well understood. So if someone could please post that here in the future, that would be great. But essentially, yes, the key fundamental idea here is that ubiquinones essentially function as a medium between a 2 electron donor like NAD and a 2 electron and a 1 electron acceptor like FMN or FAD in its partially reduced form. Okay. And then I believe this is the, oh no, there's two electron carriers that we still have to go over. So there's cytochromes and iron-sulfur groups. Iron-sulfur proteins. So cytochromes are electron carrier proteins that contain iron-containing heme prosthetic groups. So the classification of cytochromes depends on the differences in their light absorption spectra, which depends on the structure of the heme units. So this is a heme unit, and in this case, this particular heme is called heme A. This type of heme unit is called heme A, and hence we call the cytochrome A because it contains a heme A, right? Cytochrome B contains an iron protoporphyrin IX, heme B. So in the sense, we can see here that there's a slight difference. There's a bit of a difference between the two structures. So we can see here that compared to heme B, heme A has an aldehyde, and heme A also compared to heme B has a long hydrocarbon chain. Now the hemes of cytochromes A and B are tightly but not covalently bound to their associated proteins or cytochromes, right? Now, oops, I don't know what happened. Just 1 second. All right. Now for cytochrome C, the heme unit here is covalently attached to its associated protein through cysteine residue. So a cysteine residue covalently attaches to heme unit C, or heme C, via sulfur cysteine bridges. Yeah, that would make sense. Yeah, so yeah, there's sulfur bridges. So a cysteine amino acid forms a covalent bond with one of the sulfur atoms attached to the heme C. Okay. And this is heme B. Alright, and that's pretty much it for the cytochrome electron carriers. Now, the last form of electron carriers are the iron-sulfur proteins. So, iron is associated with either the sulfur atoms, which are a part of the cysteine residues, or they're associated with inorganic sulfur atoms that are not attached to anything. And then the last option is that iron could be associated with both sulfur atoms that are a part of cysteine residues, or they're they're associated with sulfur atoms, as shown here in this diagram. Right. So we see here that cysteine bonds to this iron atom through a sulfur, and then the same thing happens with this sulfur here. They both form a bond with the cysteine residue. And then the key idea here is that that iron-sulfur proteins actually participate in one electron transfers where only one iron atom is oxidized or reduced. All right. Now, before I end things off, one second. This thing is glitching. Before I end things off here, let's just take a quick glance at the importance of this. So we see here that in oxidative phosphorylation, the last process of the ETC, the last process of cellular respiration, we see here that there are a bunch of electron carriers present here that participate in redox reactions, most importantly NAD and FAD, as well as the cytochromes. All of these electron carriers I described here earlier today, or all of these electron carriers that I described here in this video, are all participating in redox reactions one way or another. Right? So this is essentially just a brief summary of what we went through today. Alright. So next time what we'll be doing is we'll be going through the process of glycolysis and all the individual biochemical reactions that occur.